Okay, so we're continuing the conversation with position, velocity, speed, and acceleration. For this problem, they're asking us find the acceleration due to gravity. Okay, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronomer David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is s of t is equal to negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds, as shown in the figure right. What is the ratio of the Earth's gravitational force to the moon? Okay, so we're talking about the gravitational force of the moon is another way to talk about acceleration. But the only thing I'm given is the position function. So I'm going to have to remember back and see how can I use my position function to get me acceleration. Luckily, I remember that a of t, aka my acceleration, is equal to the derivative of velocity, which is also the same thing as the second derivative of position. So let's go ahead and start applying it. If I know that s of t is equal to negative 0.81 t squared plus 2, then I can use that information to figure out that s prime of t, also known as velocity, would equal, according to the power rule, negative 1.62 t. The derivative of 2 is a constant, so it's a 0, so it disappears. All right? So now if I take the derivative of again, which means I'm taking the derivative of velocity, I end up with a nice negative 1.62. And that number, I need to take into account the units. Okay, so they were talking about the fact that this was going to be the height in meters. S of t is the height in meters, and t is the time in seconds. So it should be, okay, so the blue, my units were meters. But then I took the derivative with respect to time, so then my velocity should have been meters per second. So if I take the derivative of my velocity, I should get meters per second squared. So that means that for the moon, this is my constant gravitational force. Now, because I'm also a giant nerd, I know that the Earth's gravitational force is negative 9.8 meters per second squared, or negative 16 feet per second squared, because America. However, they're asking for the gravitational ratio of Earth's force to the moon. Because this one's in meters per second, I'm going to stick with the meters per second as well. So to answer this question, it's negative 9.8 divided by a negative 1.62, which I'm going to leave it as 9.8 over 1.62. I'm sure if I wanted to, I can simplify that down, but I'm a pass. And that's how you use your relationship between position, velocity, and acceleration in these problems. As long as you remember this relationship, you should be good to go with most of these problems.